So here the next part of the discussion is allotropic forms of oxygen. In this we have two allotropic forms, one is O2 and the other one is O3. So if you go for O3, that is O3 is nothing but ozone. If you take ozone, it is triatomic gas. It is in the pure form, it is pale blue. It is pale bluish in color. In liquid it is violet color. Violet color, and finally turns to, that is violet black solid. If you take, then if you go to the ozone, it is highly unstable molecule, highly unstable, so more reactive. So if it is more reactive, highly unstable, more reactive, it means that this O3 molecule, you can just that means it decomposes. If it is more reactive, means you can say that O3 gas decomposes to give O2 gas, and it releases one nascent oxygen. This nascent oxygen indicates that it is powerful oxidizing agent. Smaller quantities, it is harmless. It acts as a filter for ozone layer. It acts as a filter for UV rays. So that means the UV rays which are coming from the stratosphere, that is UV rays coming from the stratosphere. If you take this ozone which is present in the stratosphere, it converts the ultraviolet radiations to, that is infrared radiations, that is plus O2 gas. So it is very clear that the ozone which is present in the stratosphere, it will convert the harmful UV radiations to the harmless infrared radiations by release of oxygen gas. So if it is present in smaller quantities, that is maximum permissible limit is only up to less than 10 ppm in its concentration. So in higher concentration level, it is very dangerous. It may affect biologically it may affect the human cells. So that's why maximum permissible limit is only up to 10 parts per million, and it acts as a filter in the conversion of harmful radiations to harmless radiations. Then it is also used in that is filtration of potable drinking water. If you go to the structural aspects of ozone, go to the structural aspects. If you take, it is the resonance hybrid molecule, triatomic molecule. So you can take one double bond oxygen with the coordinate covalent bond. So you have still one unpaired electron. You still have one paired electron on the central atom. So this is the first structure, and this is the second structure. Of course, you have the 3 lone pairs of electrons on one oxygen, double bond, and here also a lone pair of electron. So here 1 2 3 4 5 6, second resonance structure. So finally you're going to get, that is oxygen. This is the resonance hybrid of the ozone molecule. So here this also proves that ozone, if you take the bond order of ozone, that is total number of bonds surrounding the central atom, divided by number of adjacent atoms will give you 3/2 is equal to 1.5 is the bond order. So preparation, next part of the discussion, that is preparation and properties of ozone, chemical properties, that is chemical properties of ozone. So here if you go to the preparation of ozone, actually we take O2 gas, reversible reaction, you find that here O3 gas is produced, and here balance the equation, take 3, take 2 here. So and here you find that sufficient amount of heat, it's an endothermic process, plus of heat, this is silent electric discharge, endothermic process, silent electric discharge occurs, and the formation of ozone, here we can say formation of ozone is endothermic reaction, point number 1. Point number 2, here you find that the ozone obtained, O3 obtained is called ozonized oxygen, in which only 10% of O2 is converted to O3. 10% of O2 is converted to O3, and if you go to the feasibility of formation of ozone, you are finding that here if you take O2 gas, that is 3 moles of O2 gas is converted to 2 moles of O3 gas, it means that 2, that means 2 moles of O2 consumes 2 moles of O2 is giving 3 moles of O2 is giving 2 moles of O3. So from reactants to products, if you carefully observe, you find that 3 moles are converted to 2 moles, means here you can take, that is 3 volumes of O2 is converted to 2 volumes of O2. So you find that here I can say that from this there is a decrease in the volume decreases, entropy change in the molecules also decreases, and when the entropy change decreases, randomness also decreases. So that means it is very clear that here, suppose if I apply the equation delta G is equal to delta H minus T into delta S, it is very clear that the formation of ozone, it is obeying the Gibbs-Helmholtz free energy equation, wherein which here delta G, here from this equation it is very clear that delta G is positive, enthalpy is positive. If enthalpy is positive, then T into delta S is negative. It means that definitely, because enthalpy change is positive in the formation of ozone, definitely it's an endothermic process. The process is endothermic, non-spontaneous, and if it is non-spontaneous, definitely delta G is positive. If it is positive, then it is not feasible, because very little amount of the reason for only little amount of ozone is obtained from the oxygen is because here the delta G value is positive, non-spontaneous, endothermic, and the free energy, when the randomness decreases, entropy decreases with respect to temperature, then enthalpy change is positive, endothermic reaction, then delta G is positive. If delta G is positive, the reaction becomes non-spontaneous. At the same time, if you go for, that is decomposition of, that is if you go for the feasibility, let me say feasibility of formation of O2 from O3. In other words, you are trying to decompose O3 from, you are trying to decompose O3 such that it gives O2. So what is happening here, if you take O3 gas, reverse that reaction to O3 reversible reaction O2. So here 3 moles of O2 gas and 2 moles of O3 gas. So 2 volumes, I can take here 2 volumes of O3 gives you 3 volumes of O2. You are finding that there is increase in the volume. It means that the volume increases from reactants to products. When volume increases, entropy change becomes positive, randomness increases, then enthalpy change becomes negative, then delta G also becomes negative. If delta G is negative, then the reaction is spontaneous. If the reaction is spontaneous, then I can say that delta G is also negative. So therefore we can say that therefore the reaction is also exothermic. Decomposition of ozone is always exothermic. The reaction becomes spontaneous, delta G is negative, enthalpy is negative, free energy is negative, and entropy is also positive. So the volume increases from reactants to products. So in this way we can make a comparison between the formation of O2 from O3 and preparation of O3 from O2. In both the cases, that means the decomposition of ozone is reverse of formation of ozone. Formation of ozone is endothermic reaction, whereas decomposition of ozone is exothermic reaction. Decomposition of ozone is feasible. Spontaneous. That's because the free energy change of the reaction is negative, but in the formation of ozone, the free energy change is positive. So the reaction becomes non-spontaneous, and delta G is positive, and it is going to be endothermic reaction. So now let us go to the actual chemical properties, that is chemical properties of ozone. So I can say that O3 is a powerful oxidizing agent because it is unstable and highly reactive. So you can take here O3 upon decomposition, it gives O3 gas. Upon decomposition gives O2 gas plus one nascent oxygen. So therefore here we can take some oxidizing properties. So take some oxidizing properties. What are the important oxidizing properties of O3? Important oxidizing properties of O3 if you take, that is PBS, which is lead sulfide, which is black, and here sulfur is -2. Sulphite, you treat it with the O3 gas, it converts the lead sulfide to lead sulfate, wherein which here the sulfur is this is -2 of +4, so this sulfur is +6 sulfate, and you get oxygen gas. So here if you take 4 moles and here if you take 4 moles, the reaction is balanced, and this is used in restoration. Lead sulfate, this is white, lead sulfate is white, lead sulfide is black and lead sulfate is white. So this is used in restoration of old oil paintings. Restoration of old oil paintings. So this is number 1. Number 2, we can just take that is potassium iodide. When treated with the O3 in the presence of H2O, dilute H2O, you can, iodine is -1, so here you are going to get I2 plus KOH plus O2 gas. So here what we have to understand here is, because it is iodine, so take 2 over here and take 2 over here, so the number of oxygens are already balanced. So there are 4 oxygens, so here the iodine is 0. So again here the ozone is acting as an oxidizing agent, here also O3 is acting as an oxidizing agent. It is converting the I-2, that is I2, and oxygen gas is released. This I2, actually this reaction is used in, so again take the I2 obtained I2 is again treated with the sodium Na2S2O3, okay, to give, that is Na2S4O6 of 2NaI. Actually this is violet in color, iodine is violet in color, and this iodine gets consumed and it is going to give sodium tetrathionate. Sodium tetrathionate is the main product which we get, and here it is plus 2.5 is the oxidation state. So here it is plus 2.0. So therefore here again iodine is acting as an oxidizing agent, and actually here it loses the color, the solution becomes colorless, so that's why we can say that it is used in the estimation of iodine, in other words iodimetry. This is one particular case of the oxidizing property of ozone where we can keep it in mind. Now go for the third case. If you go for the third case, that is tailing of mercury. Tailing of mercury, if you take mercury, yes, mercury is the liquid metal. You know that mercury is the only metal which is in the liquid state, so mercury is a liquid metal, lustrous, and it has shining nature. So once the ozone molecule Hg, when it is treated with O3, Hg solid when it is Hg liquid, when it is treated with the O3 gas, it loses its meniscus, it becomes Hg2O plus O2 gas. So balance the equation, take 2 over here, it loses its meniscus, the shining nature of the metal, it loses its meniscus, loses its meniscus, and it forms Hg2O. Again the mercury can be regenerated again by washing it with water. So the same Hg2O, if you add it with water, then immediately you find the mercury is obtained, and you're going to get here, that is H2O2 peroxide is obtained. To balance the equation, yes, you can just take 2 over here, and this is liquid. Just we are trying to wash the mercurous oxide. The mercury is again regenerated in the second step. So the first step indicates that mercury is losing its meniscus and its lustrous nature and shining nature by formation of mercurous oxide, and the same mercurous oxide, from the mercurous oxide you can regenerate mercury by adding water. So here the same tailing of mercury, you can also show it in another way. You know very well that oxygen is a good oxidizing agent, so O3 gas gives rise to O2 gas plus nascent oxygen. Let this be the first equation. Take the mercury, which is liquid, pass the nascent oxygen, it forms the that is Hg2O. So to balance the equation, take 2 over here, let this be equation 2. Now you add both the equations, so nascent oxygen gets cancelled, so 2 moles of Hg liquid plus nascent Hg O3 gas gives rise to Hg2O plus, that is O2 gas. This is nothing but mercurous oxide. So this is called the tailing of mercury. In this way also we can prove that the tailing of mercury is taking place. This part also we can prove that it is tailing of mercury. So here the next part of the discussion is, that is addition reactions of ozone. If you take, this is nothing but test for unsaturation of alkenes and alkynes. Alkynes, and we can also call this as reductive ozonolysis. reductive ozone lysis. What is the reagent we are using? O3 in the presence of Zn of H2O. This is the reagent which we try to use. So therefore here you can take alkene, that is take ethylene or ethene. Ethene, when treated with the O3, it forms a cyclic compound. Both the bonds are broken, and you can find that CH2 again CH2, you get an ozonide. This is called ethene ozonide. We call this as ethene ozonide, and for this ethene ozonide, if you go for ethene ozonide, this when treated with zinc in the presence of H2O, so the bond is going to break symmetrically like this, and you are going to get here, that is 2 molecules of CH2O plus CH2O. You are going to get CH2O plus CH2O plus H2O2 is the byproduct, and these 2 molecules, they are called as formaldehyde molecules. So if it is formaldehyde, you can just take the structure as, that is hydrogen single bond, carbon double bond, oxygen single bond, hydrogen is the formaldehyde structure. So this is in the case of alkene. Ethene means this is nothing but alkene. So now let us go for, ethene is alkene. So now let us go for, that is alkynes. This is A and this is for B. If you go for B, CH triple bond, CH plus O3. If you take, yes, here we are going to get CH, again ozone is added with 1 molecule. So this is ethine ozonide. This is ethine, alkyne, ethine ozonide. Ethine ozonide. So this, upon treatment with the Zn in the presence of H2O, the bond breaks symmetrically like this. So the bond remains intact with the carbon and hydrogen, and you are going to get, that is CHO single bond CHO plus H2O2, where we call this molecule as glyoxal or 1,2 ethane diol. 1,2 ethane diol is the final product which we are going to get in the addition reactions. So this comes under the, this comes under the addition reactions of ozone, and we have some tests, actually tests for ozone. Test for O3. If you go for test for ozone, one is, you can take tailing of mercury. If you take where mercury in the presence of O3 gives you mercurous oxide, then starch Ki paper in the presence of O3 is converted to I2, that is violet color. Benzidine paper, ozone, it converts to brown. Benzidine paper, it converts to brown, and you can also see that formation of ozonite. Alkenes, alkynes, when treated with O3, they forms respective ozonides. So all these are the tests for the O3 molecule in giving different colors. So now the next part of the discussion is, that is allotrophy of sulfur. If you go for allotrophy of sulfur, sulfur has 2 to 3 different types of allotrophic forms. S alpha, S beta, and S gamma. This is rhombic sulfur, monoclinic sulfur, rhombic sulfur, monoclinic sulfur, plastic sulfur, sulfur. So if you go for S alpha and S beta, S alpha and S beta, if you take the difference, S alpha is rhombic sulfur, this is monoclinic sulfur, monoclinic sulfur. Here this is pale yellow, and this is pale yellow, and of course this is also more or less it is dark yellow, we can say dark yellow. And here if you go for acid molecule, it is insoluble in water, but soluble in carbon disulfide, alcohol, benzene, etc. Then it has a crown structure, puckered ring structure, puckered ring with the S8 molecule. Its atomicity is 8, S8 molecule. But if you go for the monoclinic sulfur, it is stable. So here the next part of the discussion is that is it is stable. The monoclinic sulfur is stable at 95.6 degrees centigrade. So that means as long as the temperature is below or equal to 95.5 degrees centigrade, it is stable and it exists in the monoclinic form. But if the temperature increases, so I mean to say you find that there is an equilibrium being established. So S alpha to S beta, if the temperature is greater than 95.5 degrees centigrade, it gets converted to, that is monoclinic sulfur less than S beta to S alpha. I can take S beta to S alpha. Here I'll take S alpha. So if the temperature is greater than 95.5 degrees centigrade, it converts into monoclinic sulfur, and if the temperature is less than 95.5 degrees centigrade temperature, it again converts back to monoclinic sulfur. And here this temperature, that's why we can call this as, therefore it is this temperature is called transition temperature. This temperature we call it as transition temperature. So here what is happening is, what we are noticing here is, yes, here also monoclinic, that is monoclinic sulfur also, it has puckered ring, structure, puckered ring, S8 molecule, it is S8 molecule, and yes, it is highly soluble in carbon disulfide, and insoluble in water. So suppose, for example, and one more thing what you have to notice is, what we have to notice is S alpha or S beta. Suppose if I am taking S alpha, when you heat it to a very high temperature of greater than 700 degrees centigrade temperature, if this S alpha is octatomic S8, so S8 is first converted to S6, and S6 is finally converted to S2. Here S6 we call it as angel sulfur. S6 is called angel sulfur. Actually monoclinic sulfur, it exists in the fine needle-like, it has fine needle-like crystals. Upon cooling it dissolves in carbon disulfide, and it acquires, that is chair form structure. So if you want to show the structure of both S8 and S6, if you want to show the structure of S8 structure, it is a crown like structure. So you can just take it like this: sulfur and again sulfur, again sulfur and sulfur. This is somewhat like a crown shaped structure. This is a crown shaped structure where you can find all the sulfurs. Each sulfur has 2 lone pairs of electrons. Here one lone pair, lone pair, lone pair. Wherever you go, you find 2 lone pairs like this. For acid molecule, this is crown structure. Crown structure, and its covalency is 2. Each sulfur covalency is 2, and the bond length, the bond angle is bond angle if you take approximately 102 degrees, and the bond length will be same in all the cases. And if you go for angel sulfur, that is S6, it acquires the chair form, so you can just take it like this, chair form. This is the chair form structure, that is sulfur, 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 sulfur and sulfur. This is the chair form structure of angel's sulfur. So this is chair form. This is the chair form structure. So I repeat, here the bond angle in acid molecule is not 102, it is 107 degrees, and here the bond length is 206 picometers. 206 picometers, and here the bond length, it is 102 degrees. 102 degrees, and here the bond length is 2.204 picometers. This is the bond length between the 2 sulfurs in the case of, that is the crown structure of acid molecule, and also S6 molecule, that is angel's sulfur. The next part of the discussion here is, that is preparation and properties, preparation and properties of SO2. If you go for preparation, if you are going for the preparation, that is sulfur solid when treated with oxygen gas, upon heating you get directly sulfur dioxide gas. This is one way of preparing the sulfur dioxide, but in the industrially, this is the simple method preparation. Industrially we can prepare the sulfur dioxide by taking the pyrite ores. Take the pyrite ores, take the pyrite ores, and you subject it to roasting. You pass it O2 and you subject it to roasting. You get the sulfur dioxide gas. So let us see what kind of roasting we can done here. That is iron pyrites FeS2 when it is treated with oxygen gas, subjected to roasted, so you get Fe2O3 plus sulfur dioxide gas is obtained. Balance the equation, 11 oxygens you can take. 11 means here you can take that is 22 oxygens, means I think if I take here, that is 2 sulfurs are there, so take, suppose if I am taking 2 over here, 2 means, suppose 11 oxygens means, suppose if I am going to take 4, 8 plus 4 is 12, so suppose if I am going to take 8, 4 if I take 4 sulfurs, if I am going to take 4 sulfurs, then take 2 over here, then 4 sulfurs, so take 4 over here, 4, 8 plus 6, that is, so here 4 moles of iron sulfide reacts with 11 moles of oxygen gas to take, because 4 moles of iron means 2 to 4, and here we have 4 to 8 sulfurs, so take 8 over here. So 8 if you take, 11 2s are 22. Yes, the reaction is balanced. So this is iron pyrites when they are subject to roasting, you get that is hematite, oxide ore of iron, and sulfur dioxide is released. Similarly, if you take zinc blend, ZnS zinc pyrites, when you treat it with oxygen gas, yes, it is subjected to roasting, and you are going to get here zinc oxide plus sulfur dioxide gas. zinc oxide solid plus sulfur dioxide gas we are going to get. Yes, we can balance the equation. So like here we have 2 and here also that is 2. Then sulfur, if you take 2 over here, so take 3 here, the reaction is going to get balanced. So similarly, if in the laboratory, in the lab method we can directly take, that is sodium sulphite aqueous when treated with HCl, aqueous dilute. Yes, we can get, that is sulfur dioxide gas plus sodium chloride plus H2O liquid aqueous we can obtain. This is lab method. This is, you can also take sodium bisulfite and again you can treat it with the, yes, balance the equation. I think the reaction is not yet balanced, so take 2 over here and take 2 over here. I think the reaction is balanced. 2 plus 1 3 oxidants, yes, it's balanced. So therefore take HCl, again aqueous dilute HCl. Yes, you can get SO2 gas plus NaCl plus H2O is the gas which we are going to get, and this is aqueous. In this way we can prepare the sulfur dioxide through lab method, and industrially we can prepare, and also normal method of preparation also we can. So here if you go to the properties of SO2, it is that is, if SO2 if you take, it is colorless gas, highly soluble in water, liquefied at minus 10 degrees centigrade, and at minus 76 degrees centigrade it condenses to a white snow solid, and this sulfur dioxide, it's a good reducing agent. It's a very good reducing agent in moisture, and here it behaves as both, it can behave as both Lewis acid as well as Lewis base, because of the presence of lone pair of electron on the sulfur, and because of the incomplete octet in the case of sulfur, we can easily say that it can act as a Lewis acid as well as Lewis base. And when hydrolyzed, this sulfur dioxide gas, upon hydrolysis it gives us acid, and this sulfur dioxide gas can be tested by passing chlorine gas, which becomes SO2Cl2, which we call it as sulfuryl chloride, which is very poisonous gas, sulfuryl chloride, and it gets oxidized to, SO2 gas gets oxidized to, that is V2O5, in the presence of vanadium pentoxide acting as catalyst, it gets oxidized to SO3 gas. It's an exothermic reaction which obeys the Le Chatelier's principle. So if you go for chemical properties, in the chemical properties of sulfur dioxide, if you take, first one is this sulfur dioxide when it reacts with a base, that is NaOH is a base. When it reacts with the sulfur dioxide, it forms sodium bisulfite, sodium sulfite plus H2O. It gives sodium sulfite plus H2O. So if you want to balance the equation, take 2 over here, the reaction gets balanced, so it gives it. So take the sodium sulfite and you add SO2 gas plus H2O liquid. If you take, I think we can get sodium bisulfite aqueous, sodium bisulfite aqueous. So balance the equation, take 2 over here, 6 oxygens. Yes, the reaction is balanced. So here what we are able to understand is, that is sulphite. Again, when it is treated with sulfur dioxide, the sulfur dioxide converts the sulphite to bisulfite. This is bisulfite. So likewise, if sulfur dioxide gas, if it is hydrolyzed in water, reversible reaction, it is going to give an us acid. Aqueous, it is an us acid. Sulfurous acid. Now sulfur dioxide is a good reducing agent, so here Fe3 plus SO2 plus water, which is acting as a good reducing agent, so it gets reduced to Fe2 plus SO3 plus H plus ions. So suppose if I am going to take 4 H plus ions, take 2 over here, I think the reaction has to get balanced. Suppose if I am going to take, total 4 oxygens are there, so this is plus 2 and this is plus 3. Reducing agent, sulfur dioxide is getting, all reducing agents, they get oxidized, so it is like this, that is sulfur is plus 4 oxidation state, and here sulfur is plus 3 plus 6 oxidation state. Balancing the equation, actually what is happening here is, you can take SO2 gives rise to SO3, so there are 2 oxygens and here there are 3 oxygens, so take 2 H2O, here you can add 1 H2O. So when you add 1 H2O, then you should also add 2 H plus ions, then 2 H plus ions, then here we can take, that is number of electrons have to be charged, because this is, here sulfur is plus 4 and this is plus 6, it is getting oxidized, so the number of electrons should be added on the product side. So therefore let this be the first equation. Go for the second equation, Fe3 plus gives rise to Fe2 plus, so this is reduction, so add the number of electrons here. You add 1 electron, number of electrons added in the reactant side must be equal to, number of electrons added in the first equation must be equal to number of electrons added in the second equation. So therefore in the second equation, if you multiply it with 2, so this is going to become, this is 2 electrons plus 2 Fe3 plus gives rise to 2 Fe2 plus, if I take, so 2, here also I am going to take 2, then here if you are taking the equation, let this be equation 3, so if you add both, then you will come to know how many number of hydrogens are possible here. Yes, total that is 2, 3. Suppose if I am taking here 3 oxygens are there, so if I am going to take 2 H plus ions, I think the reaction has to get balanced, because we have 2 3s are 6 positive charges, 2 2s are 4 positive charges, another 2 positive charges. The reaction is already balanced here. So this proves that the sulfur dioxide is definitely acting as a good reducing agent. So this is ferrous, this is ferric ion, and this is ferrous ion. Yes, the reaction is also balanced here, and likewise this is how the sulfur dioxide is acting as a good reducing agent. And if you go for the next reaction, similarly permanganate ion, if you take permanganate ion, add the sulfur dioxide, which is acting as a reducing agent in the presence of water, gives rise to Mn2 plus Mn2 plus SO3 plus H plus ions. So here I think if you are taking number of oxygens, we have 6 are there, 6 plus 1 7 are there. So to balance the equation, I think here if I take 8 H plus ions, then this is 4. If you take 4 plus 2 6 plus 4 10, So I think you can balance the equation. I repeat, so if you take, that is permanganate ion, when you treat it with the sulfur dioxide in the presence of H2O, I think you can get Mn2 plus 1 sulfate ion plus H plus ion. So take here 5 moles of sulfur dioxide, so here also 5 moles of sulfate. So if that is the case, we have almost in the product side we have 20 oxygen, so 10 we have, and here we have 4, that is 16 means another 4. If you add 4 means, suppose if I am going to take 4 moles of H2O, then this is 8 moles of protons we are going to get. Balance the number of charges. If you are going to balance the charges, yes, we have 8 positive charges and 2 positive charges, 10 positive charges and 10 negative charges. 8 positive charges and 2 positive charges, 10 positive charges, 5 to 10 negative charges, then 1 permanganate ion, still 1 negative charge is there over there. So here if I am going to take, that is 2H2O, and here this is going to become 4 H plus ions, then if I can take 2 here and 2 here, I think now the reaction can get balanced, because we have 2 negative charges and here we have 4 positive and 4 positive, 8 positive, 10 negative, 2 negative, 2 negative. Just the reaction, the entire reaction is balanced here. So this is permanganate ion, this is plus 7, and this is manganese ion, and this is sulfate. Here the sulfur is plus 4, reducing agent, and here the sulfur is plus 6, which is oxidizing agent. So therefore these two reactions are the excellent reactions where we can prove that sulfur dioxide is a good reducing agent. Apart from that, sulfur dioxide, it's a reducing agent in moisture. It's a reducing agent in moisture. So bleaching of SO2 is through reduction. SO2 gas, 2 moles of SO2 gas plus 2 moles of H2O liquid always gives H2SO4 aqueous plus 2 H plus ions, 2 nascent hydrogens. You can take 2 nascent hydrogens. So this nascent hydrogen shows the bleaching property. This nascent hydrogen shows the bleaching property. The next part of the discussion is, that is oxy acids of sulfur. So we have 2 types of acids. One is us acids. If you go for us acids, you can take H2SO3, H2S2, H2S2O3 you can take. Then if you this, we can call it as sulfurous acid, thiosulfurous, acid. And in the same us acids, we can take H2SO3, take 2 moles, you just heat it, remove 1 molecule of water, you get H2S2O, H2S2O5. That is Pyro. This is Pyro Sulphurous acid. That means 2 molecules of acid if you take, and if you heat it, when you're heating, 1 molecule of water is lost. So that's why we are using the word pyrosulfurous acid, or you can also call it as disulfurous acid. Disulfurous acid. Then take this disulfurous acid, H2S2O5, and again you remove 1 more oxygen from it, then you get H2S2O4. This is hyposulfurous acid. Then so therefore now if you take all these structures, that is H2S2O2, sorry, this is H2S2O2, so H2SO3, H2S2O2, then H2S2O5 and H2S2O4. If you take the structures one by one, First one, it is H2SO3 sulfurous acid. Take the sulfur, so it has two OH groups, it is dibasic and it has a lone pair of electron. So this is the structure of the sulfurous acid, which is almost pyramidal in shape, wherein which the sulfur undergoes sp3 hybridization, and it is dibasic. So you can see that here one proton is released and here also one proton is released, so it is dibasic. Going for H2S2O2, if you take, that is Thiosulfurous acid, if you take, so here you get a thio group, sulfur double bond sulfur, then here you get two oxygen and hydrogen bonds. So again you have a lone pair here, you have a lone pair. So here this is positive, this is negative, and this is positive and this is negative. So here what is happening here is, again this is pyramidal in shape, thiosulfurous acid, it is dibasic. Then comes H2S2O5, H2S2O5. This is also dibasic acid. Yeah, this is also dibasic acid. So only thing is that we have sulfur of sulfur linkage. So we have one OH group. Here also we have one OH group. Then we have double bond oxygen. Here also we can take double bond oxygen, but we have one lone pair like this. So it is something like it has a pyramidal structure. So here also this is the pyramidal structure, H2S2O5. Then next comes H2S2O4. Then we have two lone pairs. So H2S2O4, two lone pairs. If you take, this is, so again sulfur to sulfur linkage, we have two oxygen hydrogen bonds. Of course here it is dibasic, here also it is dibasic, and one negative and one positive, one positive, one negative, one positive and one negative. So here we have a double bond oxygen. Again here also we have a double bond oxygen, here also we have a double bond oxygen. So here this is the structure where we can show for H2S2O4. So all this comes under the acids of sulfur, that is Oxy Acids of Sulphur. So sulfurous acid, thiosulfurous acid, pyrosulfurous acid or disulfurous acid, hyposulfurous acid. Now the second part of the category of ic acids, that is now we have ic acid series of oxy acids of sulfur. So here we can take, first one you can take H2SO4, this is sulfuric acid, and B you can take that is H2S2O6 dithionic acid. Of course this is a thionic group. You can also add H2S2O3 thiosulfuric acid. I am also adding one more, that is H2S2O7. Okay, so now what I can say is, like, I want to go like this: take two molecules of sulfuric acid and you heat it, remove one molecule of water, you get over here, that is H2S2O7. So this is pyrosulfuric acid, also called oleum. Pyrosulfuric acid called oleum, and this pyrosulfuric acid, if you take, if you remove one more oxygen from this, we can take this as H2 S2O6, H2S2, yeah, O6, and this is going to become hyposulfuric acid. Hyposulfuric acid and the dithionic acid, they are almost same, so no problem, just we can carry out. Actually like we can say dithionic or disulfuric, polythionic is also there. Apart from this, instead of dithionic, what I can say here is like disulfuric acid. If you take disulfuric acid, I think you can take H2SN, S of polythionic. I can just convert this to polythionic, N plus 2 I will write here, N plus 2, and I will write this as polythionic. So this is going to become hyposulfuric acid. Also we have, apart from this, we also have, now take this H2SO4. So take the H2SO4, one molecule of H2SO4. If it is added with one nascent oxygen, you are going to get H2SO5. This we call it as peroxy mono sulfuric acid. Peroxy mono sulfuric acid, also called, it is Carr's acid. And also without removing any water molecules, if you directly add, that is H2S2, okay, you got H2S2O7. So take this H2S2O7, if you add one more nascent oxygen, you get H2S2O8. We call this as peroxy disulfuric acid, or you can call this as Marshall's. You can call this as Marshall's acid, peroxy disulfuric acid or Marshall's acid, H2S2O8. So if you go to the structural aspects of sulfuric acid, H2SO4 is sulfuric acid, H2SN O6 is polythionic acid, H2S2O3 thiosulfuric acid, then H2S2O7 pyrosulfuric acid or oleum, then H2S2O6 is hyposulfuric acid. Then here H2SO5 is peroxy monosulfuric acid, and H2S2O8 is peroxy disulfuric acid or Marshall's acid. So here let us go to the structural aspects. If you go into the structural aspects of the oxy acids, so first I am going with the sulfuric acid, H2SO4. Take the structure, sulfur double bond oxygen with one oxygen single bond, again oxygen single bond, plus of minus. So this is tetrahedral in nature, where the sulfur undergoes sp3 hybridization, the oxygen state is +2, so it is dibasic acid. This is the structure of H2SO4. Then coming back to, that is H2SO4, then I am going with the H2S2O3 polythionic acid. We can do it in the last. Take H2S2O3 that is thiosulfuric acid, H2S2O3 thiosulfuric acid. If you take, yes, it contains one thio group first of all, so take one oxygen hydrogen bond, single bond hydrogen, take one positive charge, take one negative charge, positive negative, and H2S2O3, no, so already it's over. If there is no more oxygen, so you can create one lone pair, and here you can just show the negative charge and the positive charge. Now coming back to next H2S2O7, that is pyrosulfuric acid or oleum. If you go for pyrosulfuric acid or oleum, if you take, that is CH2S2O7, if you are taking, then you find that we have an odd electron, we have odd oxygen here, so sulfur, oxygen, sulfur oxygen and sulfur, OH bond, here also OH bond we can take. Then here we have one double bond oxygen, here also we have double bond oxygen, 3, 4, and this is also 4. So you find that here so this is lone pair of electron, so this is Okay, so yeah, this is also, so this is the structure of the H2S2O7, and the oxidation state of sulfur is +6 in both the cases, because one of the oxygen is trying to bind against each other. Then I am going to show you the structure of H2S2O7 somewhere here. We have a peroxy bond here, that is, let me show the structure of the H2S2O8. It contains one peroxy bond. It contains one peroxy bond. So if you take the peroxy bond, sulfur, oxygen, oxygen, sulfur, one alcohol and one more alcohol, it contains, and here one double bond, here one double bond, here one double bond, and here one double bond. So here you find that this is the the tetrahedral nature. This is also the tetrahedral nature, and this is the peroxy bond where you find. So in peroxy bonds, -1, this leads to peroxy character. Because of the peroxy bond, the sulfur oxygen state cannot exceed +6. That also we have to keep it in mind. So we have done H2S2O7, we have done H2S2O8, we have done H2SO4, we have done H2S2O3, and still remaining, that is H2SO5. This also contains the peroxy bond. So here I can take the H2SO5. Okay, here I have a space. So what I'm going to do is take H2SO5 structure. If you're taking H2SO5 structure, take the structure. So sulfur, it contains one peroxy bond, OH, single bond, double bond oxygen, again double bond oxygen. So it is tetrahedral in shape. It contains one peroxy bond here, so you should make a note of that. So this is going to become the peroxy bond in the structure, -1 peroxy bond. This is the peroxy bond of that is peroxy monosulfuric acid, that is Carros acid, and the 4 hydrogens, and it has tetrahedral shape. So the Carros acid also we have done. The only thing which is left is, that is H2S2O3. I think H2S2O3 also we have done. Thiosulfuric acid we have done here. Yes, this is also completed, H2S2O3. So except polythionic acid, rest of all we have done. So polythionic acid is not that important yet, just we can leave that and we can finish off the remaining cases. So all this comes under the weak acids of sulfuric acid. So the next part of the discussion here is, that is preparation and properties of that is sulfuric acid. So this H2SO4, actually it is called oil of vitriol or king of chemicals. It is called king of chemicals because because of its large applications, wide number of applications in the industrial in the industries. The sulfuric acid has large number of applications. That is the reason we call it as the king of chemicals. And this sulfuric acid can be what are the properties of sulfuric acid? It is colorless liquid, highly soluble in water, highly soluble in water due to hydrogen bonding. It dimerizes, and this sulfuric acid, when you go for sulfuric acid, handling of sulfuric acid, H2SO4, when it is coming in contact with water, the reaction is highly exothermic. So therefore you should add more amount of water. Acid should be acid is mixed with large quantity of water in excess, followed by slow stirring. This is because water is a good sulfuric acid, it's a good dehydrating agent. And there is a chance for the mixture to explode. That is why the acid, that is H2SO4, is slowly stirred along with water, slow stirring, so that the heat distribution is uniform. Apart from this sulfuric acid H2SO4, if you take, it is a strong acid, aqueous, it is dibasic, so it gives 2 H plus ions plus 1 sulfate ion. It is dibasic, strong acid, it is dibasic because it is giving 2 H plus ions. If you go for the preparation, many methods are there for preparing the sulfuric acid. That is, normally industrially we can prepare, that is iron sulfide. When treated with oxygen, you get sulfur dioxide gas plus Fe2O3 ferric oxide. So take here, take 2 moles here, take 2 moles here, this is 8 moles and this is 11 moles of gas. So take the sulfur dioxide gas and again you treat it with the oxygen gas in the presence of vanadium pentoxide catalyst at 2 bars of pressure and 720 Kelvin temperature reaction conditions. You get 2 moles of SO3 gas and large amount of heat is generated. So this equilibrium therefore follows the Le-Chatelier's principle. Wherein which you are finding that there is a decrease in the number of volumes in the reactant side. Here you find that there are 3 volumes and here you find only 2 volumes. So when there is decrease in volumes, according to the Le-Chatelier's principle, decrease in volume will increase in pressure, and that leads to decrease in temperature. So the obtained SO3, obtained sulfur trioxide gas is again in turn mixed with the sulfuric acid to give H2S2O7, that is oleum, fuming sulfuric acid, and this fuming sulfuric acid again, when it is hydrolyzed with water, diluted, you are going to get, that is 2 molecules of sulfuric acid, which is 98% pure. This is the reaction which is taking place, and this we can just take this as, that is contacts process. We can take this as contacts process. So let us go to the chemical properties. Let us go to chemical properties of sulfuric acid. So here H2SO4, it's a good it's a good dehydrating agent. And it is also good oxidizing agent. It is oxidizing agent because its oxidation state is +6. It's an ec acid. All ec acids usually they are good oxidizing agents. If it is dehydrating agent, it has to remove water, removal of H2O. If it is oxidizing agent, then it has to oxidize the lower oxygen state compounds to the higher oxygen state compound. So I am going to take it like this, H2SO4 as dehydrating agent. As a dehydrating agent, if you take, there are 2 reactions where you can take H2SO4 acting as a dehydrating agent. C12H22O11, this is sugar. When you add concentrated H2SO4, it acts as a dehydrating agent minus H2O, and it forms, that is carbon. This is that is nothing but charred sugar. charged sugar, nothing but charged sugar, which is nothing but carbon. This is carbon left. Or you can just write the reaction like this: C12 H22 O11 in the presence of concentrated H2SO4 carbon plus, that is H2O. If you take, so to balance the equation, 11 if you take, and this is carbon, this is charred carbon, you can take. This is dehydrating agent. Apart from this, you can even dehydrate the ethyl alcohol. This is alcohol. If you add concentrated H2SO4 at a temperature of 170 degrees centigrade, yes, one molecule of water is eliminated. It forms alkene, it forms ethene, and it removes water. So this is as a dehydrating agent. Now we will go for H2SO4 as oxidizing agent. So it will oxidize copper to copper sulfate plus 2. It will oxidize carbon to carbon dioxide plus 4, carbon to carbon dioxide plus 4. Then likewise, so if you take these two reactions, if you are taking this two reactions in particular, that is copper when treated with the sulfuric acid, you get copper sulfate plus sulfur dioxide plus H2O. Then I think if you are taking 4, 6, 4, means suppose if I am going to take 2 over here, I think there are 4 hydrogens, so take 2 over here. Yes, the reaction is already balanced. It is acting as an oxidizing agent. So copper is 0, oxidation state here, the copper is plus 2. Yes, the reaction is justified. So therefore copper is converted to copper sulfate. Here also, if you take carbon, when it is treated with sulfuric acid, it is acting as an oxidizing agent. So you get carbon dioxide plus sulfur dioxide plus H2O. So here the carbon is 0, here the carbon is plus 4. So therefore we can say that it is acting as an oxidizing agent. If you take sulfur, also it's a non-metal. So sulfur when reacts with the sulfuric acid acts as an oxidizing agent. So sulfur is 0, so it gets oxidized to sulfur dioxide plus 4 and it gives water. So that's why I think if you take 2 over here, I think if you're going to take 2 over here, I think the reaction gets balanced. But yeah, we can have 2 if I take, suppose if I am going to take 4, total 8 are there. So 8 means if I take 3 here, 3 moles of sulfur, yes, I think the reaction is already balanced. Yes, the reaction is balanced. Then likewise, sulfuric acid H2SO4 reaction on salts of say Mx. So if Mx is the salt, M plus of X minus plus H2SO4 you can take, that is Hx plus Hx plus M2SO4 is the new salt. So this is something like a new acid is formed. This is an acid. When it reacts with salt, when it reacts with salt, it gives new acid, and it gives a new salt of the similar character. So this is Mx. So here the next part of the chapter is, that is 17th group, halogens. So in this halogens, why they are called as halogens? They are halogens because the word halo means salt forming nature. They have salt forming tendency. Second is they are 17th group or 7th A group seventh A group elements, that is P block. They belong to P block and their general electronic configuration is ns2 np5, which is because number of valence electrons in halogens, if you take, that is valency electrons, number of valence electrons is equal to 7, and the valency, the group valency is equal to, that is group number minus 8, which is equal to 7 minus 8, which is equal to minus 1. Minus 1 is the group valency. So if that is the case, then what are the elements which we can consider the halogens? So if you take the elements, for example, if you are taking the elements if you take, that is fluorine, atomic number 9, chlorine, atomic number 17, bromine, atomic number 35, fluorine, bromine, iodine is, again you add that is iodine is 53, for 35 you add 18, you get 53, and astatine, fluorine, bromine, iodine, and astatine is 85. 80 is astatine. Here F is fluorine, then chlorine, then bromine, then iodine, and last one is astatine or astatine. So here, if you go for the general electronic configuration, helium of, that is 2s2 2p5, and chlorine is neon of 3s2 3p5, bromine is argon of 3d10 4s2 4p5, then helium, neon, argon, krypton 4d10 5s2 5p5, then helium, neon, argon, krypton, xenon 4f14 5d10 6s2 6p5. So you are finding that here, the last 7 electrons are entering into, that is ns orbital and np orbital. So therefore the general electronic configuration of the 7th A group family is definitely ns2 np5. So if you go for the general properties discussion, that is general properties, if you go for the general properties of halogen, general properties of halogens, you take fluorine, chlorine, bromine, iodine and astatine. Actually fluorine and chlorine, these are non-metal gases, non-metal and metallic gases. Bromine is a liquid non-metal, and iodine is sublime solid and sublime solid non-metal, and astatine is a radioactive solid, radioactive metal. And if you go for the colors of the astatine, here if you go for colors, different colors, you go for colors, fluorine is pale yellow, and chlorine is greenish yellow color, bromine red color, reddish brown, iodine is violet color. So different halogens have different color formation tendency because they try to absorb the different spectrum. For example, there is one reason why the fluorine is showing, what is the reason the fluorine to show pale yellow color, and what is the reason for iodine to show violet color. In the electromagnetic spectrum, if you take fluorine being small size, if you go for the fluorine, it has so many unique properties. Fluorine, if you take, that is smaller atomic size, fluorine has smaller atomic size, then it has low bond enthalpy, high oxidizing power, then this fluorine, it is highly electronegative, then it has highest standard oxidation potential, which is equal to plus 2.86 volts. It has absence of d orbital. So all these points you have to keep it in mind. And interestingly, what is happening here is fluorine, because of its smaller atomic size, fluorine gas always try to absorb the smaller size. That's why it will try to absorb the radiation. If you go for the electromagnetic spectrum, violet, indigo, blue, green, yellow, orange, red. Red has maximum wavelength and minimum energy. And if you go for violet, if you take, it has minimum energy, minimum wavelength and maximum energy maximum. So because of its large size, iodine, because of its large size, it will try to absorb. Fluorine, because of its small size, it will try to absorb the radiation of it absorbs the red color radiation. Absorption is red, but when it gives yellow color. Yellow is the complementary color. Similarly, iodine is very large, so it will try to absorb the red color. Iodine is trying to absorb, so it will try to absorb the violet color. It will try to absorb the same situation is taking place here, different complementary colors. So the same explanation you can give for iodine, which is violet color. So this violet and yellow, these are complementary. These colors are called complementary colors. So because of the vacant orbital present in their atomic orbitals also, they can easily, that is, accept the radiation and make the electron to get excited, and they can acquire the new color formation. And this is the reason why we say that the halogens have different color formation. So if you go for the halogens, because sources, let me continue with the topic, that is, they are called as halogens because they have the mineral or salt forming tendency. Mineral salts or salt of minerals forming tendency. That's why they are called as halogens. So if you take the different mineral ores of fluorine, chlorine, bromine and iodine, so they have different sources. For example, if you take calcium, if you take fluorine, it is available in the form of fluorspar, then 3Ca3PO4 taken twice of CaF2. This is called fluorapatite. Then chlorapatite, 3Ca3PO4 taken twice of CaCl2. Then you can take it as chlorapatite. That means here you are finding that chlorine is present over here. Here fluorine is present. Then you can take KCl. That means, for example, if you take fluorine, Na3AlF6. Na3AlF6 is nothing but cryolite, which is an important mineral ore. Then you can take carnallite, KCl, MgCl2, 6H2O is available in the form of carnallite. Then you can take NaCl, which is brine solution. It's called as brine or rock salt. Then NaIO3, then NaBrO3. We can call them as seaweeds, so on and so forth. So these are all some of the important sources of the mineral ores of the halogens, depending on their availability. And if you go for the periodic trends, periodic trends in halogens, so for example, if I am taking the first case, that is electronegativity, if you take decreasing order of electronegativity, yes, halogens, if you take fluorine has the highest electronegativity, so fluorine is more electronegative than chlorine, is more electronegative than bromine, is more electronegative than iodine. In fact, we consider the fluorine as the superhalogen. We consider it as superhalogen. It has high enthalpy of hydration, high enthalpy of hydration, and on Pauling scale, its electronegativity value is equal to 4.0. Bond energy, if you go for bond energy in halogens, if you take in halogens, that is chlorine is greater than, bromine is greater than, fluorine is greater than iodine. So here chlorine is greater than bromine, bromine is greater than fluorine, fluorine is greater than iodine. Here you are finding that fluorine has less bond energy than that of chlorine and bromine. It is because of the reason that is it has that is non-bonding, because F2 being small in size. The reason is small in size, and if you go to the actual structure of fluorine, it has non-bonding pair of electrons. So it has all the 3 lone pairs. Each fluorine is having 3 lone pairs. So you find that there is abnormal electron repulsions taking place. Electron repulsions of lone pair of electrons takes place. So as a result, instead of gaining more energy, the fluorine will try to show very less energy, and it is also having, that is absence of d orbital. One more reason is it has absence of d orbital, and its enthalpy of hydrogen is very high. So that is the reason why you find that abnormally the fluorine gas has lowest bond energy than that of the chlorine and bromine. Then if you go for the last one, that is electron affinity, if you take in the halogens, if you are taking in the halogens, then yes, chlorine is greater than fluorine, fluorine is greater than bromine, is greater than iodine. So you find that chlorine, electron affinity of chlorine is greater than the electron affinity of fluorine because of the less electron repulsions. Though the chlorine is having more or larger atomic size, you find that in the chlorine less electron repulsions takes place than the fluorine. But fluorine, because of its small size, more electron repulsions takes place. So therefore it cannot release more amount of energy when it is trying to gain one electron. Actually, the electron affinity property of all the halogens can be studied through the Born-Haber cycle. In the Born-Haber cycle, we will first convert the molecular halogen to atomic halogen, and that atomic halogen, it will try to gain an electron and it forms the uninegative ion. Once it forms a uninegative ion, it is involved in the electron affinity, and once it is involved in the electron affinity, some amount of energy is released during the formation of uninegative ion. That uninegative ion can be shown here. That is, if you go for electron affinity, that is, if you take half mole of chlorine gas, by supplying a bond dissociation energy, it becomes atomic chlorine gas. This atomic chlorine gas, now it gains one electron and it forms uninegative gaseous ion. So this is electron affinity. Then enthalpy, this uninegative gaseous ion, when it is dissolved in water, it becomes Cl minus of aqueous. So therefore enthalpy of hydration involves. So that means various energy changes are taking place such that you are converting the molecular form of the chlorine gas to the aqueous form of uninegative chloride ion is converted. So series of steps takes place, and this proves that the electron affinity for chlorine is much more greater than that of the fluorine. So fluorine, because of its small size and more electron repulsions between the non-bonding pair of electrons and the bond pair of electrons, surprisingly you find that the fluorine will have lesser electron affinity than that of the chlorine. So therefore you can find this kind of order in the case of halogens. And if you go for the other cases, like apart from that, I think I can add one more, that is, if you take the oxidizing power among halogens, if you take also, yes, fluorine is considered as a superhalogen. So next comes chlorine, next comes bromine, and next comes iodine. So therefore it is proved that even in the reactivity series in the electrochemistry, in the reactivity series also, you find that all the non-metals are placed at the bottom of the reactivity series, which has the positive standard that is reduction potential, and all the metals which are more reactive, metals which have more reactivity are more reducing in their nature. So all the highly reactive metals are placed at the topmost position of the reactivity series, and all the non-metals which are having the highest SRP value, which are more oxidizing in nature or which have more oxidizing power, are placed at the bottommost region of the reactivity series. And you know very well that fluorine is the only element in the entire periodic table which has the highest electronegativity. More is electronegativity, more is the oxidizing power. So when you go for more oxidizing power, you can say that fluorine is placed at the bottommost region of the reactivity series, and it proves that definitely here because of the various exceptional reasons, anomalous reasons, fluorine is definitely more oxidizing than the remaining halogens or their counterparts of halogens. So here the next part of the discussion is, that is, if you go to the chemical properties of halogens. If you take, let us discuss something about the oxidation states. If you take the oxidation states, that is, we all know that the general electronic configuration of the halogens is Ns2 Np5. So like if I am going to take, that is, I'll consider the Ns2 Np5 as, suppose if I am taking Ns2 Np5, if you take Ns sublevel or orbital, it contains 2 electrons, and if you take Np5, if I am going to take, that is 1, 2, 3, 4 and 5, this is Np5. Of course it has 5 electrons and it has 2 electrons, and this Np5 you can just write it in the form of, that is Px, this is Py and this is Pz. But here what you are noticing here is it contains 1 unpaired electron. So when it is having 1 unpaired electron, if I consider this as, this configuration as ground state, because it contains 1 electron, then I can say that the oxidation state of the halogens, of all halogens in the ground state, we can consider it as, that is either +1 oxidation state or -1 oxidation state. If I take the +1 oxidation state, for example, if I take +1 oxidation state, we can take for example, you can take Cl2O. The best example for +1 oxidation state is, you can take chlorine monoxide. -2 is the oxidation state of oxygen, valency of oxygen is -2, so chlorine is +1. For -1 oxidation state, you can take that is you can take halo acids. If you take halo acid, you find that the fluorine definitely shows negative oxidation state. And even if you take the interhalogen compounds, like not only this, you can also take ICl. If you take ICl, yes, chlorine is -1, so the iodine is carrying +1 oxidation state. So this two cases you can take it in terms of, that is +1 and -1 oxidation state, that is +1 and -1 oxidation state. So I can say that these two comes under, that is, both are having +1 oxidation state. Iodochlorine and dichlorine monoxide is having +1 oxidation state, and in hydrogen fluoride, fluorine is having -1 oxidation state. And now I want to transfer or promote one of the electron from Np orbital to Nd orbital, and this is the ground state configuration. Go for the next case, that is now promoting one electron. So I am going to take again Ns2 electrons. If I take, so there are 2 electrons here, then here, that is 1, 2, then this is 1, 2, 3, 4, 5. So this I can take it as Np5, this is Ns2, and this is Nd. Okay, this I am taking it as Nd0, but right now I am going to convert this to first excited state. If it is first excited state, then already we have 1, 2, 3, 4, 5 electrons are there. So one of the electron from the Np5 orbital, you try to promote it to Nd orbital. So if that is the case, then that means the new configuration, that is, we have to promote it. So still it is in the ground state only, the same ground state I have taken. So I'll just take this as the ground state configuration, take this as ground state. Now convert this to excited state. In the excited state, I can take again Ns2, that is 2 electrons, again go for and now this is going to become NP4 with 1, 2, 3, 4. This is px, this is py, and this is pz orbital, and one electron is promoted. So here 1, 2, 3, 4, 5. So this is one electron, so this is going to become ND1. So and this is going to become first excited state configuration. But interestingly, what you're noticing here is we have 3 unpaired electrons. Here we have one unpaired electron, here we have unpaired electron, and here also we have unpaired electron. So what are the oxidation states which are possible here? We can take +3 oxidation state. You can take +3 oxidation state. The oxidation state is +3. So if it is +3 oxidation state, then what are the examples you can take here? Examples you can take, the best example is ClF3. The best example is ClF3, that is interhalogen compound trifluorochloride. The oxidation state of chlorine is +3, and you can also take the oxy acids of chlorine. You can take, that is oxy acids of chlorine. You can take HClO2 also, chlorous acid, which is +3 oxidation state. So these are the 2 examples where we can give for +3 oxidation state. And next from here we will go for the next oxidation state, that is you promote one more electron from px orbital to the Nd. This is dxy. Let us take this as dxy. This is dyz. So if it is dyz, then this is going to become, the next configuration is going to become, that is ns2 of 2 electrons. Take the promotion of electrons 1, 2, 3. So this is going to become np3. Now if it is np3, so therefore now this is px, py, and this is pz. So therefore you borrow one more electron to the nd2. Now this has become nd2, 1, 2, 3, 4, 5. So take 2 electrons here. So right now you have, this is dxy and this is dyz. This is dyz, and now this has become the second excited state configuration. If it is second excited state configuration, you are finding that the total number of unpaired electrons in the given orbitals are 3 plus 2, total 5. So here the oxidation state can be +5. If it is +5, again you can take one the +5 oxidation state. Yes. So here you can take some examples. Here for +5 oxidation state, you can take BrCl5, wherein which the bromo group is +5 oxidation state, and you can also take, that is chloric acid, which is again +5 oxidation state. So we have one more configuration, that is the third excited state. If you go for the third excited state, let me explain here the third excited state. That is, I can take here, yes, you can promote one electron from the ns2 configuration to nd2. So this is going to become, that is first orbital is ns1, one unpaired electron, then np 1, 2, 1, 2, 3, then this is nd3. So 1, 2, 3, 4, 5. So 1, 2, 3. This is nd3, and here it is np3. So therefore this is px, this is py, this is pz, and this is dxy, and this is dyz. So what is happening here is like we have 7 unpaired electrons, 1, 2, 3, 4, 5, 6, and 7. So therefore this is the third excited state, and it has oxidation state equal to +7. So the examples of the +7 oxidation state, you can take number of examples you can take. That is, the best example is, that is IF7 interhalogen compound, in which iodine is +7. Perchloric acid, the oxidation state is again +7. Perchloric acid, HClO4, and you can also take chlorine heptoxide, wherein which the chlorine is having +7 oxidation state. So it's starting from -1. That means, in a nutshell, how do you conclude this? In the conclusion, you can take, that is starting from -1 to, that is +1 to +3 to +5 to +7. Oxidation states are possible in the case of halogens. So the least oxidation state for the halogens is -1, and the maximum oxidation state for the halogens is +7. So therefore various cases of -1 to +7 already we have studied. -1 oxidation state is possible in the case of ground state, and +1 oxidation state is possible in the case of the third excited state, and these are the corresponding examples what we have taken in the case of least oxidation state to the highest oxidation state. So if you go to the next part of the chemical property of halogens, that is you can go for, that is solubility of halogens. If you take solubility of halogens follows the order, decreasing order, that is decreasing order of solubility among halogens. If you take, that is fluorine is more soluble than chlorine, is more soluble than bromine, is more soluble than iodine. Iodine, because of its large size, the iodine is almost insoluble in water. But if you take fluorine, in the case of fluorine, that is fluorine gas when reacts with water, under cold conditions, you can take HF gas plus O2 gas. This is one reaction where you need to remember. So balance the equation. So that is, we have 2 oxygens, so take 2 over here and take 4 over here and take 2 over here. And if the same fluorine gas, if it is reacting with water under hot conditions, in the case of steam, so you find that here, that is HF gas plus O3 gas. So here balance the equation, take 3 over here, then take 6 over here and take 3 moles over here. That means you are finding that fluorine, when it is coming in contact with water, fluorine when it is subjected to hydrolysis, or when it is trying to get soluble in water, it is giving the mixture. This mixture is called, that is ozonized oxygen. But if you go for that is the rest of the halogens, that is chlorine and bromine in particular, chlorine comma bromine, if you treat this as X2, then if this X2 gases, X2 when reacts with water, they give 2 types of acids, one is HX and HXO. HX is called as halo acid, these are called halo acids, and HXO, that is hypohalites. These are called as hypohalites. Then for example, if you take chlorine in particular, chlorine gas when it reacts with water, it forms HCl plus HClO. And similarly, if you take bromine, Br2 plus H2O gives rise to HBr plus HBRO, hypobromous acid. And this is hypochlorous acid, and this is hypobromous acid. So here, if you go for the next part of the discussion, apart from the solubility, if you take in the solubility, if you take particularly I2, note one important point what we have to note down here is, that is I2 is a sublime solid, and I2 as a solid, if you put it in water, liquid, it is insoluble. Because the solubility is expressed in terms of free energy, which is positive, and it is non-spontaneous. Iodine, because of its large size, it is insoluble in water. So that's because the change in free energy of the solubility of the iodine is positive, which is non-spontaneous. But however, you can increase the solubility of iodine by treating it with the potassium iodide aqueous. When treated with iodine solid, it forms Ki3 aqueous. Here the solubility increases. This Ki3 forms K plus of I3 minus Ki3 minus. This is a soluble complex. And this I3 minus has, if you take I3 minus ion species, this is triiodide species, wherein which if you take the structure of triiodide, then this is going to become, that is something like you have 3 iodines in the same plane with a negative charge, and we have 3 lone pair of electrons for the iodine, and it undergoes sp3 hybridization, the sp3d hybridization. Here the iodine undergoes the sp3d hybridization, and the 3 lone pairs are occupying the equatorial plane, and the shape of the molecule is going to become linear shape, where the 3 lone pairs are trying to occupy the equatorial plane. So this is the structure of I- ion, and that comes in that way we can increase the solubility of, that is I3 Ki3 minus ion of the Ki3 salt. So if you go for the displacement reaction, the next part of the chemical properties, displacement reactions in halogens. Suppose if I am taking one reaction like this, that is Kx plus F2 gives rise to, that is Kf plus X2, where fluorine is acting as an oxidizing agent. So here is X2 is 0. So it is very clear that now X2 is a halogen, and here the halogens are chlorine, bromine and iodine. Then again what we are noticing here is, you take K of X plus Cl2 gas, again it's an oxidizing agent, so you find that this is KCl plus X2 gas, so here you find that here, that is X2 is equal to, that is chlorine means that is bromine comma iodine only. Of course you need to balance the equation, take 2 over here, that is 2 fluorine, so take 2 over here, take 2 over here. And the last one, if you take, that is again, if you take Kx is nothing but potassium halide here. Kx is called as potassium halide, and take this potassium halide, and now if you are treating it with bromine aqueous, then you find that here, that is KBr plus X2 gas, where X2 is equal to iodine only, bromine KBr aqueous. That means from these 3 reactions, what you are able to understand is, that is, you can just take it as the decreasing order of oxidizing power. OP stands for oxidizing power among halogens. Among the halogens, if you take, yes, you can take fluorine is greater than chlorine is greater than bromine is greater than iodine. So that means what is happening here is, fluorine, if I am going to take fluorine, chlorine, bromine and iodine, if I am going to take, and you find that fluorine can oxidize chlorine, it can oxidize bromine, and it can also oxidize iodine. But at the same time, if you take chlorine cannot oxidize the fluorine, but however chlorine can oxidize the bromine, and it can also oxidize the iodine. Similarly, if you are going to take fluorine, chlorine, bromine and iodine, if you take, yes, bromine can oxidize iodine, but you cannot bromine cannot oxidize chlorine, bromine also cannot oxidize fluorine. So therefore bromine can oxidize only iodine, because iodine is at the bottom of the bromine. So bromine can oxidize iodine, but bromine cannot oxidize chlorine and fluorine. Similarly, if you take chlorine can oxidize bromine and iodine, but chlorine cannot oxidize fluorine. But if you take fluorine can oxidize all 3, chlorine, bromine and iodine. So this method of oxidizing, that means this method of oxidizing, the method of oxidizing less less oxidizing halogen by more oxidizing halogen by more oxidizing halogen is called as displacement reaction. So here the next part of the discussion here is that is reaction with the H2 gas, reaction of halogens with the H2 gas. If we take, that is, you can take the reaction that is H2 gas, when it reacts with X2 gas, it gives HX. HX is nothing but a halo acid. It's a halo acid. HX is halo acid. So if you go for HX, so you find that here HF, HCl, HBr, HI. So what are the periodic trends? If you go to the periodic trends of halo acids, if you take in this, the first one you can take, that is melting point and boiling point. Melting point comma boiling point of halo acids, usually it is directly proportional to the increase in the atomic size of halogen and also that is increase in van der Waals forces and also that is hydrogen bonding. These are the three characters which you have to keep it in mind. So if you go for the the melting point and boiling point, if you take the decreasing order, HF is much more greater than HI, is much more greater than HBr, is much more greater than that is HCl. Why this variation is coming in the case of the melting point and boiling point for the halo acids? Actually, if you take hydrogen fluoride is an associated liquid. It has hydrogen bonding. And it also shows the dimeric nature. Only HF has the tendency to form the dimeric nature, and that is why we can say that hydrogen fluoride has the highest boiling point and melting point. And if you go for HI, it is having after HF, it is HI because the molecular weight or the atomic weight of iodine also it is very high, and the rest of the halogens you're finding that there is decrease in the van der Waals forces. So this is one trend which we have to keep it in mind. The next comes after this, you can go for that is the B bit. If you take this next part of the discussion, if you make the increasing order of acidic strength, so here acidic strength is directly proportional to lesser bond energy between hydrogen and halogen. And the ability for the given halo acid to release the proton is also one important point which you have to keep it in mind. So the increasing order of acidic strength means HF is less acidic than HCl, is less acidic than HBr, is less acidic than HI. So I can say that HI is strong acid and HF is a weak acid. HF is weak acid since it has strong bond energy. It has strong bond energy between hydrogen and fluorine. There is a strong bond energy. So therefore it with great difficulty it is going to release the proton. But in the case of HI, you find that because of the large size of iodine, you find that it has weak bond energy. So therefore we can say that hydrogen iodide is HI is the strong acid and HF is the weak acid. So therefore you know very well that always weak acids give a strong conjugate base by release of proton according to the Bronsted-Lawrence theory, and strong acids always give weak conjugate bases by release of proton. So therefore since HF is a weak acid, so its conjugate base is going to become F minus plus H plus ion, and if you go for Hi, which is a strong acid, gives I minus plus H plus ion. So therefore, what the best thing what we can do is, because the hydrogen fluoride is a weak acid, so you can take F minus is a strong conjugate base. So I can add one more, the increasing order or the decreasing order of the strength of conjugate base. If you take Cb stands for conjugate base, so F minus is a stronger conjugate base than Cl minus is stronger conjugate base than I minus. Apart from this, you can take the thermal stability and the bond energy and the bond enthalpy. If you take also thermal stability, it again depends upon the hydrogen and the size of the halogen. So therefore, thermal stability of HF is much more greater than thermal stability of HCl is much more greater than HBr is much more greater than Hi. So all this we can keep it in mind in terms of the hydrates of halogens. So the next part of the discussion here is action of alkalis on halogens. Actually, every halogen has different mode of reaction with the alkalis. For example, if you take fluorine in particular, that is so when you are going for action of alkalis means, I mean to say here alkali is NaOH, or you can take KOH, sodium hydroxide or potassium hydroxide, any one you can take, and you can treat it with halogen under different conditions. You can take cold case and you can also take hot case, and let us see what is happening, what kind of products we are going to get when these halogens, when they are going to react with the alkalis like sodium hydroxide or potassium hydroxide. So here, if you are taking particularly if you are going to take fluorine gas, so I am going to take fluorine gas, and if I am going to take NaOH is cold and dilute. So if I take fluorine gas in the cold and dilute state, so then interestingly you are going to get sodium fluoride plus oxygen difluoride plus that is H2O. Okay, so to balance the equation here, I think if I am going to take, that is 2 over here, that is total number of fluorine atoms, 2 fluorines and 2 fluorines, 4 fluorines are coming over here, and the number of sodiums are 2. Okay, fine, so I am going to take 2 over here. Then I think if I am going to take hydrogens and 2 oxygens are balanced, and the number of fluorines also, yes, they are automatically balanced, and this is called oxygen difluoride, in which the oxidation state is, that is +1 is the oxygen state, and here it is that is 0. So indirectly I can say that the sodium hydroxide is acting as an oxidizing agent, and this is cold case. Now if you go for the same fluorine gas in the case of sodium hydroxide, that is in the case of hot case, then you find that yes, sodium fluoride you are going to get plus O2 gas plus H2O. Yes, directly we are getting oxygen gas over here. That is the difference we should try to make out, and we have 2 hydrogens and 2 okay, to balance the equation, say suppose if I am taking 2 over here, then I am going to take 4 over here, then because you have already 4 hydrogens and 4 oxygens are there, that's why taking 2 moles of water you get 4 hydrogens and 4 oxygens, so take 4 over here. So therefore take 4 over here again, then you take 2 over here. Yes, the reaction is balanced. Then if you go for the rest of the cases, like if you go for chlorine, that is bromine and iodine, they have altogether different methods of reacting with the NaOH, that is NaOH cold and dilute, and the same NaOH that is hot and concentrated. So taking this into consideration, first I will take only chlorine. With the chlorine I am going to write the reaction. Suppose if I am taking chlorine gas plus NaOH cold and dilute, then you are going to get, this is a disproportionation reaction. It's a kind of disproportionation reaction where the chlorine is going to disproportionate from 0 oxidation state to the next higher oxidation state. So therefore here you can take sodium chloride plus sodium hypochlorite plus H2O you can take. Yes, to balance the equation, take 2 over here. Here the chlorine is -1 oxidation state, and here the chlorine is +1 oxidation state. So here this is sodium hypochlorite. Sodium hypochlorite you can take, and the same chlorine gas, if you are going to take the sodium hydroxide, that is hot and concentrated, the reaction slightly differs here. That is, you can take sodium chloride plus sodium chlorate NaClO3 plus H2O. This is sodium chlorate. So this is going to become, this is +5 oxidation state, this is -1, and this is 0. So definitely it is a disproportionation reaction. Here also it is disproportionation reaction. Balance the equation, take 5 over here, take 6 over here, and take 3 over here. Then I think the entire reaction has already been balanced. So this is a perfect example. All I can say is this is a perfect example of, that is, disproportionation reaction. It's a perfect example of disproportionation reaction, and more or less the reaction is same in the case of the bromine and iodine also. So that's why what I can do here is, yes, if you take bromine if you take with the NaOH cold, if you take, yes, you get NaBr plus NaBrO, and with iodine also more or less you get the same kind of reaction. That is, cold, if you take NaI plus NaIO, and if you take bromine, again in the presence of bromine aqueous, if you take in the presence of NaOH hot, I'm not balancing the equation, sodium bromide plus sodium bromate. And here also if you take iodine, yes, NaOH, if you take, that is hot, you get NaOI plus, that is sodium iodate, NaIO3. You can take NaIO3, so sodium iodate. Actually these NaBrO3 and NaIO3, these are called as seaweeds, which are obtained near seashore of the halogens. That's why halogens are salt producing minerals, we call them. That's why the group name is halogens. So the next part of the discussion here is, that is, reactivity with the O2 of halogens of X2. So here I can take here something like this, F2 Br F2 okay, that is, I'm going to take, that is Cl2 F2 Cl2, then Br2 and I2. So there are actually all the halogens, they form wide number of different oxides are there, but some important oxides let us going to discuss which are useful for us. So suppose if you are going to take for fluorine, I think we can take two types of oxides here. One is OF2 and the other one is O2 F2. And in the case of chlorine, if you take, yes, it forms maximum number of oxides, chlorine, that is, it forms Cl2 of O, it forms ClO2, it forms Cl2O6, and it also forms Cl2O7. If you go for bromine also, yes, it is going to form Br2O, BrO2 and BrO3. It forms dimeric form of BrO3. Yes, it forms I2O4 and I2O5. So in fact I can say that particularly if you take the oxides of chlorine, they are powerful oxidizing agents. If you take, for example, if you take OF2, that is this OF2 oxygen difluoride, here the oxygen state of oxygen is +2, and here the oxygen state of oxygen is +1. Here the oxygen state of chlorine is +1, this is +4, this is +3, and this is +7. Here also iodine is +5, and here the iodine is +4. That means you are finding that the oxidation state of halogens keeps changing from +1 to +7. For example, if you take all are good oxidizing agents, if you take fluorine, if you for example if you take OF2, if you are taking for example if you take OF2 preparation, sodium hydroxide plus fluorine in the cold condition, yes, it is going to give sodium fluoride plus OF2 plus that is H2O. So to balance the equation, take 2 over here, take 2 over here, and take 2 over here. Oxygen difluoride has been formed. So now next if you go for OF2, yes, it can form two fluorine atoms, and total 6 valence electrons are there. So it is, the bond angle is around 103 degrees. Here interestingly you find that the lone pair of electrons repulsions, the lone pair, you find that here the lone pair, the adjacent atoms, if you take the lone pair repulsions of adjacent atoms are greater than the bond pair atoms. That's why here the oxygen in OF2 oxygen undergoes sp3 hybridization, but the bond angle changes from 108 degrees to 103 degrees because of greater repulsions between lone pair electrons of fluorine to that of bond pair electrons of oxygen. So bond angle is decreasing from the 109 degrees 28 minutes to that is 103 degrees. And likewise, O2F2 also we can prepare directly silent electric discharge. It has open book structure. Then if you take Cl2, all these, the oxides of, particularly the oxides of chlorine, they are powerful oxidizing agents. The disproportionate and they form oxy acids when hydrolyzed. Then if you go for I2O5 structure, it has one IO5 link, wherein which it has 4 coordinate covalent bonds like this, I2O5. So if you look into the oxides of the halogens, you find that just like the oxides of chlorine, here the oxides of bromine also, they are good oxidizing agents. And the oxides of iodine, they are insoluble solids, and they are used in the estimation of carbon monoxide. And you find that the oxides of chlorine, for example, if you take particularly if you are going to take the oxide ClO2, every oxide is going to give its own oxy acid. For example, if you take ClO2, I think it can give 2 types of oxides upon hydrolysis. That is, it can give HClO plus HClO2. It can give, if I take then I think you can take HClO2 of HClO3. We can take here, that is, here chlorine is +4, and here the chlorine is +3, and here the chlorine is +5. That means it is trying to disproportionate, and it is trying to give 2 different types of oxy acids. One is chlorous acid and the other one is chloric acid, which different oxidation states which are available for the chlorine dioxide. For the chlorine dioxide, that we have to keep it in mind. And this is something about the that is reaction of halogens with the oxygens. And apart from this, what we can do is we can go for the next part of the discussion, that is interhalogen compounds. And before going to the interhalogen compounds, reaction of metals, there is one particular topic where the reaction with the metals. If you take reaction with metals, if you take these halogens, they try to show different types of behavior for the different types of metals. For S block elements, they have one kind of behavior, and for the D block elements, they have one kind of behavior. For example, if you take sodium, when it reacts with chlorine, yes, it gives sodium chloride. Both are monovalent. If you take magnesium, yes, it can also give the reaction magnesium chloride. Magnesium is bivalent. But if you go particularly for the metals like D block elements, for example, copper, when it reacts with chlorine, it always chooses the salt formation of the higher oxidation state salt, that is Cu2 plus. Cu2 plus cupric chloride is formed, but CuCl with this, which is +1 oxygen state, it is not formed. We give priority only for CuCl2. Similarly, if you go for iron and if it is treated with chlorine, you get FeCl3. Give priority for the higher oxidation state chloride, but not FeCl2. But one question I can give you, that is, what if the iron is going to react with HCl, but when iron reacts with, this is metal and this is acid. Metal, when it reacts with acid, it always prefers to give the FeCl2, which is having +2 oxidation state, is given the priority, but FeCl3, which is given +3 oxidation state, is not given priority. Of course, the hydrogen gas is evolved. So in the reactivity series, once the hydrogen gas is evolved, when the acid is reacting with the metal, once the hydrogen gas is evolved, the hydrogen gas which is evolved will prevent the metal salt to form to a higher oxidation state, because always the metals will have low SRP value in the reactivity series. So the evolution of hydrogen depends upon the metal salt formation with the lower oxidation state, and that is one reason where we can say only ferrous chloride is going to be formed, but not ferric chloride when the metal is coming in contact with the acid, that too particularly the T block element. So the next part of the discussion is, that is, formation of interhalogen compounds. So I can take here, that is something like this, xy. Suppose if I am taking x of y of n, if I am taking or x of a, I'll take x of a, I'll take x of a base n, where n can be 1, 3, 5 and 7 only. So here you can take x is the halogen, with the lesser electronegativity, and y, that is a, not y, sorry, this is a is the halogen with the greater electronegativity. So for example, because we are saying that that means here x is acting as a central atom halogen, and here a is acting as adjacent atom halogen. A is acting as an adjacent atom halogen. Okay, fine. So now how can we just try to, justify ourselves? So all the interhalogens with general formula with the x of a of n is given by, that is, you can take ICl, BrCl, then you can take chloro, fluorine, etc. All these are the different interhalogen compounds, and you are finding that iodine, if you compare iodine and chlorine, iodine is having lesser electronegativity than chlorine, bromine has lesser electronegativity than chlorine, and chlorine has lesser electronegativity than fluorine. So if that is the case, that is the first case. Go for the second case, that is interhalogens with the XA3. If you take XA3, the best example what I can give you is ClF3. You can take then BrCl3 or ICl3. You can take. You can even take ICl3. These are the compounds. And similarly, if you go for the interhalogens with the XA5, yes, we can take BrF5, BrCl5, and so on. The last one, if you take interhalogens with the XA7, the best example is, that is IF7, iodine heptafluoride. So now the question is, how to identify the AX3 type of molecules? I can say that here take ClF3, take BrF5 and take IF7. So ClF3, if you take chlorine trifluoride, if you take the structure of chlorine trifluoride, you can take it here as, that is it's in the it's a T-shaped molecule, so take 3 fluorines in this pattern, and the 2 lone pairs are occupying the equatorial position. The 2 lone pairs are in the equatorial position. It's a T-shaped molecule. It's a T-shaped molecule. It's a T-shaped molecule with 2 lone pairs in the equatorial position, and the rest of the 2 fluorines are in the axial position, and one of the third fluorine is again in the equatorial position. It's a T-shaped molecule. ClF3 is a T-shaped molecule. ClF3. Now go for BrF5. If you're going for BrF5, for example, how do you check out this? Actually, I don't know what is the shape or what is the, what kind of hybridization is there in it, or what is the shape or geometry, we don't know. That's why, because it's a neutral molecule, it's an interhalogen compound, so I'll use the formula H is equal to half of V plus M. V plus M I'm going to use, where H is the hybridization, V is the number of, V stands for number of valence electrons of the central atom, and M stands for the number of monovalent adjacent atoms which are present in the interhalogen compound. So therefore here, if I want to calculate, H is equal to half of, in the place of V, number of valence electrons of bromine 7 plus fluorine is 5. Okay, so H is equal to, that is 12, H12 by 2, which is equal to 6. 6 is nothing but sp3 d2 hybridization. If it is sp3 d2 hybridization, it should be octahedral, but one atom is missing. So what I'm going to do is I'm going to put it in the octahedral plane like this. So take the bromine, take the 4 fluorines like this, fluorine here, fluorine here, fluorine here, and fluorine over here. So take the octahedral plane first, assign the octahedral plane. So the best thing what I can do here is I'm going to take one fluorine over here like this, and one of the lone pair I'm going to put it in the octahedral plane like this. Octahedral plane we can put it. So this is something like square pyramidal, I can say. The shape is square pyramidal shape for BrF5 molecule, and even for IF6 also, IF7 also we can do the same thing. That is in IF7 the fluorine has H is equal to half of V plus M. So that means half of number of valence electrons of iodine 7, and the fluorine is also 7. So this is 14 by 2, this is 7. 7 means it is sp3 d3 hybridization. So pentagonal bipyramidal, if you take, so that is pentagon. First I am going to create a pentagon like this. This is a pentagon. This is a kind of pentagon. Fluorine, 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 and fluorine. Create a pentagon like this. And bipyramidal we are saying, so take one more fluorine here and cut the pyramid like this. This is the the pentagonal bipyramidal structure of iodine heptafluoride, and that is square planar bipyramidal, that is BrF5 molecule. Now if you go for the next part of the discussion, that is, I can say that preparation and properties of chlorine. If you take, that is, first we'll go with the preparation. In the preparation of chlorine, you can take manganese dioxide. When treated with the HCl, it forms manganese chloride plus chlorine plus H2O. If you take, yes, we can balance the equation. I think if I'm going to take 2 over here, then I think if I'm going to take over here, yes, we can prepare the chlorine gas. We got a chlorine gas here. And also manganese dioxide when treated with NaCl in the presence of H2SO4 also we can prepare. Of course you are going to get manganese chloride plus chlorine plus sodium bisulfate. So manganese dioxide, when treated with the brine solution, this is brine solution, and this is acid, and this is metal oxide, we are getting manganese chloride, chlorine gas, and this is bisulfate, sodium bisulfate. So therefore what is happening here is, like if you want to balance the equation, you are finding that there are 4 sulfates are there. Here we have 4 sulfates, so here also we have 4 sulfates, and here we have total 2 plus 2, 4 chlorines are there. Yes, 4 chlorines are there. Yes, 4 sodiums, balanced, everything is balanced. Fine, the already 3 methods are over. Now potassium permanganate, when treated with HCl, also we can get KCl plus that is, we can take manganese. Potassium permanganate, when treated with HCl, we get potassium chloride plus chlorine gas plus manganese chloride plus water. So suppose if I am taking here 16 moles of hydrochloric acid, then obviously I have to take 8 moles of water. Then number of hydrogens are balanced, but I think number of oxygens have not been balanced. So suppose if I am going to take 2 over here, number of oxygens are balanced, so therefore 2, take 2 over here. Then manganese also, if I am going to take 2 over here, I think the rest of the reaction is already balanced. So this is the best method of preparing, that is the chlorine gas. These 3 comes under the lab method. These are the lab methods. And we have the industrial method. If you go for the industrial method, that we call it as the Deacon's method. And in the Deacon's method, we take hydrochloric acid, when treated with the oxygen, we get chlorine gas plus H2O liquid. So here, that is cupric chloride acting as a catalyst. The catalyst is cupric chloride, and the temperature is around 723 Kelvin temperature, and this is how we prepare. This is how we try to prepare the chlorine gas using the Deacon's method. And apart from Deacon's method, that is the Nelson's method, Nelson's cell electrolytic method for the aqueous brine solution. If you take, so actually NaCl aqueous when subjected to electrolysis, it gives anode plus cathode electrodes. At anode you have the chlorine gas, and at cathode you have NaOH, and that is H2 gas. So there is an interference. Between the chlorine gas and NaOH. So therefore there is an unwanted reaction taking place. So therefore NaOH, which is obtained at the cathode during the Nelson cell process, it can give you NaCl plus NaClO plus H2O. This is the interference reaction taking place in the Nelson cell method. And these are all the different methods where we can prepare the chlorine, both through lab method as well as through the industrial method. And now we are going to study the chemical properties of chlorine. So let us go to the chemical properties of chlorine. So if we go for chemical properties of chlorine, if you take, that is, first one is action of ammonia. So 2 different types of reactions takes place when chlorine reacts with ammonia. Actually ammonia gas, when treated with the chlorine gas in excess, gives rise to nitrogen trichloride plus HCl. So 3 moles of chlorine gas you get. This is nitrogen trichloride. This is nitrogen trichloride. And now suppose if you are taking ammonia in excess, ammonia in excess, chlorine gas. So you can just take here ammonium chloride plus N2 gas, ammonium chloride in N2 gas, and here if you take 8 moles of ammonia, we can take 6 moles of ammonium chloride, and this is 3 moles of chlorine gas. So therefore you find that there are two different products which you are able to see, and this chlorine, if you take action of metals and non-metals, if you take metals and non-metals, action of metals and non-metals if you take, then we can take here, that is, suppose if it is reacting with copper when reacts with chlorine, you get cupric chloride, but not, yes, it can give cupric chloride, but it cannot give cuprous chloride. Then copper when it reacts with, that is, if you take iron when reacts with chlorine, it gives FeCl3 but not FeCl2, because FeCl3, iron has +3 oxidation state which is more stable, and in cupric chloride copper has +2 oxidation state which is more stable. If you go for non-metals, for example, if you take phosphorus when it reacts with chlorine in excess, it can give phosphorus pentachloride 4, and this is 10, so 10 moles of phosphorus pentachloride it can give. And sometimes it also reacts with the sulfur when it reacts with chlorine, it forms sulfur monochloride, and sulfur monochloride in turn, if it reacts with chlorine, it gives sulfur dichloride. So balance the equation, then you can take that sulfur dichloride is obtained. This is sulfur monochloride. Similarly, this chlorine, it can have the other properties, like even if it is reacting with the other non-metals like phosphorus, sulfur, it can sometimes even react with the hydrogen, lighter elements. If you take hydrogen, H2 plus Cl2, in the presence of HCl gas also, HCl vapor, this is chlorine gas, and this is hydrogen gas. Chlorine reacts with alkalis. Chlorine, if you take it, reacts with alkalis. Similarly, if it reacts with the action of alkalis, if you take sodium hydroxide when reacts with chlorine in the presence of cold and dilute condition, it gives sodium chloride plus sodium hypochlorite plus H2O. So take 2 over here, and sodium hydroxide, that is hot and concentrated, will give chlorine, that is sodium chloride plus sodium chlorate plus H2O, giving rise to, this is 5 moles of sodium chloride and 3 moles of chlorine gas and 3 moles of water. So it's a kind of disproportionation reaction that already we have done, no problem. Then likewise, if you take the same chlorine, it acts as a good oxidizing agent. It's a good oxidizing agent. H2S plus chlorine, sulfur is -2. It acts as an oxidizing agent. It gives 2 moles of HCl plus sulfur. So sulfur here, it is the oxidation state of sulfur is 0. So here chlorine acts as an oxidizing agent, and it converts the sulfide of hydrogen sulfide to sulfur. Sulfur dioxide gets converted to sulfuric acid plus HCl. If you take, then we have 2 chlorines, so take 2 over here and take mark 2 over here. The reaction is balanced. Here sulfur is +4 oxidation state, and here sulfur is +6 oxidation state, and here the chlorine is acting as an oxidizing agent. The chlorine acts as an oxidizing agent. Then in the next case, here also again the chlorine acts as an oxidizing agent. It converts the ferrous sulfate. Iron is +2 oxidation state, and here iron is +3 oxidation state. So here we have 3 sulfates and 2 chlorines. So therefore I am going to take 2 over here and 2 over here. Yes, the ferrous sulfate is getting converted to ferric sulfate, and in this way the chlorine can act as an oxidizing agent. And finally, the chlorine can also act as a that is it can also act as an bleaching agent. So last one, fourth one is as a bleaching agent. Chlorine when reacts with water, it gives HCl plus HClO, hypochlorous acid. This hypochlorous acid, upon it is unreactive and it is reactive and unstable, so therefore it decomposes to give one HCl molecule and one nascent oxygen. So this nascent oxygen as a bleaching agent, as a bleaching action, this nascent oxygen will try to kill the bacteria, and it is also used in purification of water, in the filtration of water and in the purification of water. The nascent oxygen will act as a bleaching agent, and it is going to kill all the bacteria present in water, and it will allow the safe potable drinking water, and it converts the colored substances also to the colorless substances through moisturizing oxidation. So the next part of the discussion is oxy acids of chlorine. So we have 4 important oxy acids, that is formula, name, oxidation state, hybridization, then structure, then number of sigma and pi bonds. So formula, if you take, that is HClO, name is hypochlorous acid, okay. Oxidation state is +1, hybridization is sp3 hybridization. Then structure, if you take, yes, you can take the structure as chlorine. If you take it as 3 lone pairs, and it has actually between oxygen and hydrogen also there is one sigma bond. There is one sigma bond between oxygen and hydrogen also. So therefore we can say that it's going to give the hypohalite ion. So therefore I can say the number of sigma bonds and pi bonds, there are 2 sigma bonds and 0 pi bonds. So formula, name, oxidation state, hybridization, structure, number of sigma bonds and number of pi bonds. So the first one we have done away. Then go for the second. If I go for the second, that is HClO2. If I take, then this is chlorous acid. It is chlorous acid and it is +3 oxidation state, and this is sp3 hybridization, and it is, take the structure of the chlorous acid. So it has 2 lone pairs. So because it is having 2 lone pairs, yes, I am going to take hydrogen single bond oxygen. So chlorine, if I take, then I have 2 lone pairs we have to get here. I mean 2 oxygens are there. So therefore that is 1 double bond oxygen we can get over here. 1 double bond oxygen we can get over here, and we have 2 lone pairs. One lone pair is shown like this and another lone pair is shown like this. So again it is the structure and shape, sp3, here sp3, and this is bent molecule. So here the structure is that is bent shape. So we have number of sigma bonds and pi bonds. We have 3 sigma bonds and 1 pi bond, and also we have 2 lone pair electrons. Here we have 3 lone pair electrons. 3 lone pair of electrons. So therefore all that what we could say here is we can distinguish them clearly what is happening here. So next if you are taking, that is the third oxy acid. If you take the third oxy acid, that is HClO3, this is chlorous acid, oxidation state is +5. Then here sp3 hybridization, this is pyramidal, and here we have the angle, that is we have same structure almost, hydrogen single bond oxygen, chlorine, so double bond oxygen, and we have one pyramidal shape. So therefore one lone pair we can find here. and we have total 1 2 3 4 sigma bonds, 2 pi bonds, 1 lone pair of electrons. Then again if you are going to take the last one, that is fourth one, HClO4. If you take, this is perchloric acid with +7 oxidation state, sp3 hybridization, tetrahedral, and the shape is going to be hydrogen single bond oxygen, chlorine. We have double bond oxygen, and double bond oxygen, and here also double bond oxygen. So 1 2 3 4 5 sigma bonds, then 3 pi bonds, and 0 lone pair electrons are there, and it is tetrahedral in shape, perchloric acid. So here what I can say is this is the strongest acid in aqueous solutions, and this is the weakest acid in aqueous solutions. It is the weakest acid in aqueous solutions, and this is highly unstable. It is weakest acid, unstable, more reactive. So if it is more reactive than hypochlorous acid, it gives one hydrochloric acid and one nascent oxygen. Perchloric acid is the strongest acid, so it gives the weakest conjugate base. And this is perchloric acid. It is the weakest acid, so it is going to give the strongest conjugate base. So what is the strongest conjugate base means? Here you can just take the reaction. HClO gives rise to ClO minus plus H plus ion. So this is hypochlorite ion is the conjugate base. And if you go for HClO4, it is a strong acid, so it has to give the weak conjugate base ClO4 minus. This is the weak conjugate base. ClO4 minus is the weak conjugate base. This is strong conjugate base, and this is going to become the weak conjugate base. Is the tendency of perchloric acid, which is giving the weak conjugate base, and tendency of the weak acid giving strong conjugate base is what we can make a comparison between the oxy acids of chlorine. And these are all the different shapes and structures of the oxy acid. So we have 2 lone pairs on each oxygen. Here also we have 2 lone pairs on each oxygen. Here we have 2 lone pairs. Here also 2 lone pairs. Here also 2 lone pairs. Lone pairs. Wherever you take oxygen, there you are supposed to show the 2 lone pairs. And this is the complete information where you can gather from the oxy acids of, that is, chlorine. So name, then oxidation state, then hybridization, and the structure, and number of pi bonds, and also number of sigma bonds. So here let us go to the next part of the discussion, that is the next chapter, that is 18th group, noble gases. So these are otherwise also called, they're also called inert gases because of their stable electronic configuration, that is completely filled electrons in their orbitals. Then these elements, they are called as zero group elements. These are also called zero group because their valency is equal to 0. Then these are also called as Eurogens because of their availability availability in atmospheric air. Then if you go for elements, if you are going for the elements, we have helium, neon, argon, krypton, xenon and radon. Except radon, rest of all the elements are the lighter noble gas elements. Radon is the radioactive element. So helium atomic number is 2, neon 10, argon 18, then krypton 36. This is 54 plus 32, 86. 86 is radon, and here the configuration is 1s2. Here the configuration is helium of 2s2, 2p6. Then here it is neon of 3s2, 3p6, and this is argon of 3d10, 4s2, 4p6, and again this is krypton of 3d10, 4d10 of 5s2, 5p6, and this is radon, that is xenon of 4f14 of 5d10 of 6s2 of 6p6 is the configuration. So therefore you are finding that except for helium, rest of all the elements, their general electronic configuration is ns2 np6. It proves that because the differentiating electron is entering into the p orbital, because the last electron is entering into the p orbital, so therefore we can call them as p block elements. These elements are p block elements, but again helium is an exception, because helium, the differentiating electron is entering into the s orbital, so helium is an exception. So except for helium, rest of all gases, ionization of the rest of the gases is very difficult, because the ionization of the rest of the gas are very difficult because of the stable electronic configuration. Large amount of energy is required, but even the helium also, you cannot directly ionize the helium. This helium is actually it's going to originate from the radioactive substance. So radon, if you take, it is radioactive, it is a radioactive element, distinctly radioactive element. So this radon, it undergoes radioactive disintegration. 86, it emits an alpha particle. So say for example, you can take 226, radium 226, if you take, it is going to emit an alpha particle. If it is emitting an alpha particle, it is going to be 84, that is polonium of 222, polonium 84 polonium of 222 plus 2He4 is the alpha particle which is generated. So here this 2He4 is the alpha particle. It is nothing but the alpha particle. This alpha particle is doubly charged helium nucleus. This is helium nucleus, and this helium, it undergoes self ionization to give He2 plus 2 electrons. And at the same time, if you go for the other properties of noble gases, they are insoluble in water. Then they have low melting points and boiling points. The reason is because they have weak van der Waals forces. And all the elements, they are monoatomic gases. Because of the presence of weak van der Waals forces, of the existence of monoatomic gases, they have low melting point and boiling point. So it was actually first the first compound of the noble gas elements, that is O2 plus of Pt F6 minus. This is dioxygen, but dioxygen of hexafluoroplatinate. The first complex was isolated, where in which it contains the oxygen gas, but later, that is Bartlett. It was actually Bartlett who has isolated the first noble gas compound. That is nothing but, the first noble gas compound is nothing but xenon hexafluoroplatinate. This is the compound which was isolated by the Bartlett, the first noble gas element, that is xenon hexafluoroplatinate. And if you go for the compounds of noble gas elements, if you're going for the compounds of noble gas elements, here particularly we should be bothered about compounds of noble gases. If you take compounds of noble gas, if you take, one is halides. In halides, if you take, you can take xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. And in the case of oxides, we have XeO3, then XeO4, then XeO2 of F2, XeOF4, and so on and so forth. These are all the different oxides of the xenon, and these are the halides of xenon. So now let us study the internal structures of the xenon difluoride and xenon tetrafluoride and xenon hexafluoride. So here, if you go to the preparation and properties of xenon compounds, you can very clearly observe that we are able to prepare all the halides of xenon. One is xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. Here, in the first case, if you want to prepare xenon difluoride, here xenon reacts with the excess of xenon reacts with fluorine at 673 Kelvin of temperature and 1 bar of atmospheric pressure to give xenon difluoride solid. And if we want to prepare xenon tetrafluoride at a temperature of 873 Kelvin and 1 bar of the atmospheric pressure, xenon and fluorine, they are in the 1:5 ratio, and it gives xenon tetrafluoride. And again, if you want to prepare xenon hexafluoride, again in 1:20 ratio, xenon reacts with the 3 moles of fluorine to give 1:20 ratio at a temperature of 573 Kelvin and 70 bar of pressure. You can see that the pressure, by the time we reach the xenon hexafluoride, the pressure is increased and the temperature is decreased. So that means in 1:20 ratio, the most favorable condition for the preparation of hexafluoride of xenon is, that is 70 bar of pressure and 573 Kelvin of temperature is what we have to keep it in mind. And when we are going for the chemical properties of the halides of xenon, we should be a little bit careful. In the case of xenon difluoride, when 2 moles of xenon difluoride are able to react with 2 moles of water, then I think it disproportionates. It's not exactly disproportionating. For example, here the xenon is +2 oxidation state, and here the xenon is 0 oxidation state. So the xenon is undergoing reduction. The xenon is trying to reduce itself from halide to elemental xenon, and you get one more fluorine, that is hydrofluoric acid, and also oxygen gas is evolved. And in the case of xenon tetrafluoride, here the xenon is +4 oxidation state, and here the xenon is +6 oxidation state, and here the oxygen is +1 oxidation state, and here the oxygen is 0 oxidation state. So this is a kind of the redox reaction. Second one is a perfect example of redox reaction. Of course, the first one also, it is a perfect example of redox reaction. The dioxide difluoride is trying to oxidize. This is acting as an oxidizing agent. It is oxidizing the xenon, which is in the +4 oxidation state, to xenon in the +6 oxidation state, and by itself it is getting reduced, because you can see that the oxygen atomic number is 0. And sometimes, interestingly, these halides of xenon, when they interact with the halides of the phosphorus, pentahalides of the phosphorus, the xenon difluoride, they act as Lewis acids. That means they are Lewis acid means electron pair acceptors, and donors means electron pair donors. That is, you can see that they act as Lewis bases. So the interactions between Lewis acid and Lewis base interaction always leads to the pair of complexes. One complex is cationic complex, and the other one is the anionic complex, hexafluorophosphate, hexafluorophospho anionic complex, and xenon fluoro cationic complex is formed. So in that way, we can also prepare some cationic and anionic complexes. And if you go for xenon tetrafluoride and xenon hexafluoride when they are subjected to hydrolysis, so this is a kind of disproportionation reaction. Xenon tetrafluoride plus 12 moles of water. Here the xenon is +0 oxidation state, and here the xenon is +6 oxidation state. So it's very clear that the xenon tetrafluoride is undergoing disproportionation reaction. I can say that this is definitely a disproportionation reaction, definitely disproportionation reaction. And yes, because +4 to 0 and +4 to +6 oxidation state is taking place, so therefore we can say that it is disproportionation reaction. But here what is happening here is there is no change in the oxidation number for xenon. In the next reaction, it is +6 oxidation state. Here also xenon is undergoing +6 oxidation state, so there is no change in the oxidation state. Here also the xenon hexafluoride, xenon is +6, and here also xenon is +6 oxidation state. So 2 moles of HF is the byproduct, and this is how you need to remember the various chemical properties of xenon. And now let us go to the structural aspects, including their hybridization involved, and let us try to study them in brief. So the next part of the discussion here is structural aspects of xenon compounds. So if we go to the structural aspects of xenon compounds, here we have different structural aspects. Like, let us go for oxides. If you go for oxides, we have XeO3 and XeO4, and also you can take XeO4, and you can take even XeOF4 you can take, and even you can take XeO2 of F2 also we can take. So how can we just identify the structure and hybridization of the given oxides of fluorine? For example, if I am going to take with the XeO3 underline xenon, apply the formula H is equal to half of V plus M. So V is the valency number of valence electrons of the central atom, and M is the number of monovalent atoms present in the oxides of xenon. So here what is happening here is like if I am going to take H is equal to half of, it is xenon number of valence electrons are 8, and oxygen is not a monovalent atom, oxygen is always a bivalent. So in the place of M value, M is a monovalent species, so because the oxygen is bivalent, so let us take the M value 0. So here interestingly, H is equal to 4, you are going to get H is hybridization, V is the number of valence electrons of the central atom, and M is the number of monovalent species present in the given molecule in its adjacent form. So H value is 4 here for XeO3, but you can find that the number of adjacent atoms are only 3. So therefore it is very clear that it forms when H value is 4, the number of adjacent atoms should be 4, but only 3 are there. So therefore that means it has one lone pair, compulsory one lone pair should be there. One adjacent atom is missing, so one lone pair, presence of one lone pair plus 6 bond pairs, because you find that here xenon has 8 valence electrons, so 6 bond pair electrons can be observed. So therefore if you go to the structure of XeO3, so you find that the structure looks like this. This is the structure of XeO3, and you can outright say that this is pyramidal in shape. You can outright say that this is pyramidal in shape. Pyramidal. And if you go for similarly next for XeO4, if you take H is equal to half of V plus M, number of valence electrons in xenon are 8, so therefore half of number of valence electrons of xenon are 8 and number of monovalent atoms are 0. H is equal to 4. 4 means it is sp3 hybridization, and it is tetrahedral. It is tetrahedral in shape. So therefore you can go to the structure of xenon. So here we can take here, that is, so this is xenon tetroxide, this is definitely tetrahedral in shape. And you have here, and one more thing, here we have 3 sigma bonds, sigma, sigma, pi, then this is pi, and this is sigma, and this is pi. So we have 3 sigma and 3 pi bonds are present in the case of the xenon tetroxide, and here we have 4 sigma, 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 and sigma. You have pi, 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 and pi bonds. So we have 4 sigma bonds, comma 4 pi bonds, which is tetrahedral in shape. And here you don't have any lone pair of electrons in the case of XeO3 and XeO4. So here also XeO4. Okay, fine. So that means we have completed the oxides of xenon. Now we'll go for XeO4 and XeO2F2. So if you go for XeO4, suppose for example if I am taking XeO4, if I am going to take, then H is equal to half of V plus M, H is equal to half of, number of valence electrons are 8, number of monovalent atoms are 4, but oxygen is bivalent, so I am taking only 4, so H is equal to 6, we are getting 6 means one adjacent atom is missing, so therefore we can say that this is square pyramidal. It has one lone pair and 6 bond pair of electrons, 6 bond pair electrons you can find. So if you go to the structure, it more or less looks like this, that is fluorine, 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 and it is in the square planar shape, and you find that one lone pair, you can just show it at the bottom, and here I mean one pair of electrons with respect to oxygen we can show at the bottom, and yes, of course the hybridization is sp3 hybridization, sp3d2 hybridization you observe in the case of the XeOF4 molecule, and XeO4 molecule we have observed. And now I think you can go for XeO2F2 also. You can take XeO2 of F2. If you take H is equal to half of V plus M, which is equal to half of, number of valence electrons are 8 and number of monovalent atoms are 2, so 2, and oxygen is not a monovalent, it is bivalent, so H is equal to, that is 10 by 2, which is equal to 5. 5 means again one adjacent atom is missing, so therefore we can take, of course the hybridization is sp3d hybridization, the hybridization is sp3d hybridization, but we have one lone pair and we have 6 bond pair electrons. So therefore if you go to the structure, you can take the structure like this, that is you can take, that is two oxygens, we can just show it like this, and 2 fluorines we can take, it is a square planar shape, and one lone pair you can show it like this, and another lone pair like this. This is square planar shape, it is square planar shape. This is what we can identify in the case of all oxides of xenon. So if you go to the halides of xenon, that is second part, halides of xenon, if you take, we have XeF2, then XeF4 and XeF6. All I can say is, like, if you go for XeF2, if I can take XeF2, I can say that xenon difluoride structural aspects, if you take in the first excited state, of xenon, it undergoes sp3d hybridization, and it gives a linear shape which contains 3 lone pairs at equatorial position and 2 bond pairs and in the axial position is what we need to remember. And overall we are calling this as linear shape. It is linear shape because the 3 lone pairs which are at equatorial position, they are separated at the rate of 120 degrees. So therefore if you go to the structure of, and if you calculate the hybridization value also, H is equal to half of V plus M, if you take, that is xenon, number of valence electrons are 8 and fluorine is number of monovalent atoms are 2, so H value is 5. 5 means it should be definitely trigonal bipyramidal shape, but because there are only 2 adjacent atoms, as already I told you, it has 2 adjacent atoms. If it is having 2 adjacent atoms, then 3 adjacent atoms are missing, so that's why we have 3 lone pairs and 2 bond pair of electrons. And if you look into this Yeah, 5 value means definitely it is sp3d hybridization, and trigonal bipyramidal shape it should have, but because 3 adjacent atoms are missing, so from here I can directly give you the structure. That is, I can take 2 fluorines in the same plane and the rest of the 3 lone pairs. They are trying to occupy the equatorial position like this. They are trying to occupy the equatorial position like this. They are in the trigonal bipyramidal plane. All I can say is yes, they have the trigonal bipyramidal plane. They have, but because they are 120 degrees separated apart, whatever the kind of repulsions are operating between the 3 lone pairs in the xenon difluoride, they are quite negligible. That's why we can say that the shape of the xenon difluoride molecule is definitely, that is, linear shape. So this is one important point which you have to keep it in your mind. So XeF2 is done. Now we'll go for XeF4. If you go for XeF4, again, yes, in XeF4, in the excited state 2 of xenon, it undergoes sp3d2 hybridization, but here only 4 adjacent atoms are there, so I can say that it has square planar shape with 2 lone pairs in the axial position, and the rest of the 4 bond pairs are in the equatorial position. They are in the equatorial position. So therefore here we can take, that is, xenon. So take the shape of the xenon here, xenon tetrafluoride. So here fluorine, and yeah, two lone pairs are there. So here we have 2 lone pairs. These are the 2 lone pairs we have in the case of xenon tetrafluoride. That's why we are calling it as, the shape we are calling it as square planar shape. Now going back to the last one, that is C, XeF6. If you take XeF6, that is in the excited state 3 of xenon, it undergoes sp3d3 hybridization. Then this is distorted octahedron. It has a distorted octahedral shape with the one lone pair and 6 bond pair electrons. So therefore here we can take the structure in this pattern, that is, because it is sp3d3 hybridization. So the best thing what we can do here is distorted octahedron. So because it is distorted octahedron, it has to lie in the pentagonal bipyramidal plane. So that's why what I am going to do here is, like, I am going to put it somewhere like this. I am going to create a pentagon like this. This is a pentagon, fluorine, and also fluorine here. So the pentagon is created, and we have one fluorine outside. So I am going to take one fluorine below like this here, and we have one lone pair also. So this we can take it as distorted octahedron is the final shape of the XeF6 molecule. And from the structure also, it is very clear that definitely one lone pair is existing in the case of XeF6 molecule. So if that is the case, then I can say like this: XeF2, XeF4, XeF6. So we have here, we have lone pairs, bond pair electrons, lone pair and bond pair electrons. So if I take here halides of xenon, so this I will take XeF2, this I will take XeF4, and this I will take XeF6 if I take. So you have to keep it in your mind that XeF2 contains 3 lone pairs and 2 bond pairs, then here 2 lone pairs and HCF4 4 bond pair electrons, and HCF6 1 lone pair and 6 bond pair electrons are there in the case of halides of xenon. So this is what you have to keep it in your mind: halides, lone pair electrons, and also bond pair electrons.